Hello, this is the first part of the chapter 6.2, and we'll talk about orthogonal bases. And in general, if we have a set of vector in Rn, we call it an orthogonal set if each of this vector is orthogonal to each other. So basically, for each, we can take dot product of every single pair in this set, and it will have a 0. And you're probably familiar with some of these bases, like for example, our standard coordinate system consisted of the vectors e1, e2, e3. If we take and multiply, because they perpendicular to each other, we can multiply them and get dot product equals 0. But they are not unique. In R3, any three orthogonal vectors will form an orthogonal set. For example, here we have a three orthogonal vectors u1, u2, and u3. But you shouldn't believe me that they are orthogonal. Let's just actually test if those three vectors, which is by the way illustrated here on the picture, are actually an orthogonal set. So, and again, all we need to do is just calculate dot product of each pair. For example, let's take vector u1 and u2. Again, we will calculate the dot product, and let's give us 0. Let's take u1 and u3, again 0. Third pair, u2 and u3, still 0. So because dot product of each pair is equal 0, we can safely conclude that that particular set is an orthogonal set. And why do we care about orthogonal sets so much? Mostly because they actually form a linear independent set and can be used as a basis for any subspace spanned by the set of these three vectors. And actually, there is a name for this. They're orthogonal and they are basis. So we will call it an orthogonal basis for the subspace W in Rn. And that's a very, very convenient set, mostly because there is a really nice formula which tells us how to calculate components of our vector y in this orthogonal basis. So basically, if we have our vector y, because it's a basis, we can express it as a set of coordinates, which will be a weight from C1 to Cp. And we can find each of these weights as a simple ratio of our original vectors y times the appropriate component of our basis vector. And that's much more convenient than any of the calculations of the basis when we tried so far. We don't have to solve any system of equation. We don't need to do much. We just use the formula and we substitute everything there. But let's just try to do that. So we have already the orthogonal basis. We'll look at the question 1. So let's just try to expand the vector y given here as a linear combination of this orthogonal set or orthogonal basis. Okay, let's start just using the formula. So for each single weight, we have a numerator and denominator, both of them are dot product. Let's be very careful about it. And let's start with a numerator. So we need to multiply our vector y by the first, second, and third vector in our orthogonal basis. Let's calculate dot product of y and vector u1. So we take our vector y multiplied by the first basis vector u1, and we get the number 11 in this case. Okay, let's try to do it with a second vector. So we will look at the second numerator in our formula. Again, the same vector y, but now we multiplied by the second basis vector, which give us number minus 12. Finally, the third one, same vector y, multiplied now by the third basis vector will give us number minus 33. Okay, we're done with the numerator in our formula. Let's look at the denominator. The denominator is quite easy because we are looking at the dot product of our basis vector by itself. So the first denominator will be a dot product of u1 to u1, which is reasonably easy to calculate, the result of 1, so that number will be 11. Now we take dot product of u2 by itself, which give us 6, and finally u3 by a dot product to itself, which give us the number 33/2. Okay, so now we have all the numbers we need to find our weights Cj and express our vector y along the given orthogonal basis u1, u2, and u3. But let's just be very careful and write down our formula fully. So basically, instead of j in the formula, we write our components 1, 2, and 3. So this is the first term, which is basically we're using, instead of j, we're using 1. So now instead of j, we're using 2, 3, and finally instead of j, we're using 3. And again, we can calculate each term. For example, here, y times u1, we already know that it's 11, and u1 dot product with u1 will give us also 11. So we have a ratio for the first component. The second ratio, again, we have minus 12 go to the numerator, and the 6 over there goes to the denominator. And finally, for the third term, we have y times u3 equal minus 33 in the numerator, and u3 dot product by itself 33/2 in the denominator. So now all it has left is just reduce the fractions, and we will end up with a rather simple expression which we composed without any solution of any equation, no reducing to echelon form. It is much more straightforward way to expand our vector into a given basis. And it's not surprising that most of the machine learning algorithm, this is how they expand. Like the first step and majority of algorithm is expand by orthogonal basis. And that's pretty much approach most of them use. Okay, and this is the first part. Next time we will expand this idea. Right now, you might want to go to the end of the chapter and try to do a couple of expression in the orthogonal basis.